All right. Can you hear me? Yes? Okay, the audio is working. Everything should be settled down. Okay, so hi everyone. My name is Squarcina. This is a work that I presented at Black Hat in August, also at Usenix, and I will also like to show it to you today. This is a joint collaboration with my friends Pedro Dao from University of Lisbon, Lorenzo Veronese from TU Wien, and Matteo Maffei. Couple of words about me. I got like my PhD at Kafoscari in 2017 or 18, I don't remember anymore, like too long ago, you know. Then I moved to Austria, to Vienna. I became a senior scientist there. I'm in love, as you can imagine, with web insecurity. Also started working with mobile stuff now. I'm an old guy. I started playing CTFs in 2009. I founded Maccheroni and also like a couple of other CTF teams along the way. Played CTF, the DEFCON finals 4 or 5 times. I wrote 5, but probably it's like 4. Now I'm the co-organizer of WeOwn, that is an Austrian team, and I'm involved with a bunch of security education projects with ENISA, Cybersecurity Austria. I also helped bootstrapping the Cyber Challenge project here in Italy in 2017. So yeah, quite a lot of stuff in the CTF world and in the research field. This is our group. When I joined it, we were like only 4 folks there. And now we grew up a lot. We are 35 people, 7 faculty members. We do all kind of cybersecurity stuff. The crypto as in cryptography, and the crypto as in like blockchain. We do formal methods, system security, and web security. I'm a WebSec guy, so for the WebSec part, we do the full range, the full spectrum of things that you can do there. So we do like usability studies, measurements. We also apply the formal methods, automated reasoning for bug finding and also for verification. We have openings, so you know, if you want to do a PhD or if you're just interested in doing an internship, we can have a chat afterwards. So you need a couple of reasons like why you should come to Vienna. Our office is there. It's at the center of the city. It's a really lovely spot. It's like 1 minute far from this place here. There is a pool in front of this church. And during winter time, like now, they remove the water, and inside there, they build up a Christmas market. And when we are tired and we don't want to work anymore, we just go there, we drink some wine, and we have fun. Yeah, despite the not so great food in Austria, compared to Italy at least, it was elected as the most livable city for like so many years in a row. So yeah, probably like the lack of high quality food is compensated with something else. It's actually a very nice place to live, I must say. We also have a CTF team. We own you. Probably like some of you heard about it. It's one of the most historical teams in Europe for sure, but probably I will say also like in the world. Started in 2004. Now it's a joint project between TU Wien, University of Vienna, SBA Research. The thing that I like to stress here is that CTFs at TU Wien are a core part of our educational offer. So we use like CTFs to teach basically everything that is security related. Yeah, so in this talk there will be a survey, like a poll for you, okay? So you will need like to scan a QR code. I wanted to make something funny. I wanted to rickroll you. But before coming here, I checked the law because, you know, I haven't been like in Italy for quite some time now. So yeah, I checked the law and I figured out that rickrolling people is a crime. So yeah, I mean, yeah, for real, like check it out. This is from justizia.it. So, you know, yeah, so no crimes committed in this talk. Every link, every QR code that I will ask you to scan is safe. We don't want to have troubles here with the cyber police, okay? Yeah. Okay, so this is a talk about cookies, not this kind of cookies. Do you know what is this logo? Raise your hand if you know what's that about. Okay, quite some people. All right, so this was my team when I was like studying in Venice, called the Cookies at Venice. If you match the date with like when I relocated to Austria, well, you can understand like why the team does not exist anymore. Someone tried to create another team called Fookies instead of cookies. Doesn't sound that good because of the Fookies part, but yeah, anyway, yeah. We are not talking about these cookies today, but we're going to talk about web cookies, okay? And cookies have a problem. Also, by the way, I have a t-shirt exactly like for this talk today. This is about, yeah, cookie crumbles, fits well. So, yeah, cookies have a problem, and the problem is called lack or weak integrity. What do we mean with this? Well, it's like the issue that allow attackers to mount stuff like session fixation attacks, login, cross-site request forgery, all possible kinds and variations of CSRF vulnerabilities and some of their application-specific bugs. There is a bunch of work in this field through the years, both in the academic world and the industrial ones, like professional conferences. But these are not, as I said, just application-specific issues, but these are all things that are encoded in the standard. If you check the standard of cookies, the RFC 6265 bis 12 now, there is a section called weak integrity, and all these things are documented there. So these are known problems, okay? Just so that we are all on the same page, let's recap a little bit what we mean with lack of integrity. We have like two main issues. First one is called cookie tossing. The other one is called eviction, cookies overflow, blah, blah, blah. So cookie tossing. So the attacker here is someone who can control a subdomain of the target, and the target is example.com, okay? The subdomain under the control of the attacker is attack.example.com. The idea here is that an attacker can set a cookie using the domain attribute, okay? Domain equal to example.com, and scope this cookie to the entire site, starting from the apex domain, example.com, to all its subdomains. And you can see that then like the cookie set by the attacker is also sent to example.com, right? That's why we say that the cookies do not follow the same origin policy. They're not bound to a specific origin, but they can be scoped to entire sites, all right? Another interesting attribute that we can discuss quickly is the path attribute. It's used in this kind of attacks because by specifying the most specific path for your destination, you can prioritize your cookies. So you can like put them before other cookies, and then like depending on what the server does, that cookie can be parsed before the other ones and then considered. Here we are in the context of SameSite attacks. So the SameSite attribute that is deemed as the universal solution against the cross-site request forgery attacks does not apply, because in the context of the same site, all cookies, no matter if they have like the same site strict, lax, or nothing, they can flow, okay, between origins. The other attack is called the cookie eviction, and that's the possibility for an attacker to drop, to delete some cookies that are stored in the cookie jar. Maybe this is not clear to everyone, but the cookie jar is that component that is in charge in the browser to store cookies for a website, okay? There are limits for cookie jars. And these limits, so there are limits in terms of like the numbers of entries that you can store there. But these limits are not specific to an origin, but they are specific to an entire site, meaning that you can only store up to like 180 cookies for example.com, attack.example.com, foo, bar, buds.example.com, and so on and so forth. Okay, so it's shared. The idea here is that there is the victim browser with the session equal to good. That's the cookie that we wanted to drop. Also notice that this is an HTTP only cookie, so we cannot read this cookie from JavaScript, okay? And then we can set 180, like in this case, 200 cookies without the domain attribute, okay? We do that from attack.example.com. We can do it like either using HTTP headers, the set cookie one, or we can do it via JavaScript, all right? Doesn't matter. And then we set another cookie, in this case, a domain cookie with the domain attribute set to example.com, And that's it. What happens when the browser visits example.com? That the previous cookie is deleted because the browser can't keep up storing like more than 180 cookies. But not all the other cookies that we injected before are sent, only the last one, because all the other cookies, x0 to x199, they are bound to the specific origin of the attacker. And only one is scoped to the entire site. So at the end of the day, you have only one single cookie that is the one injected by the attacker that is sent to the target. Okay? Also notice that the HTTP-only attribute is good for confidentiality against XSS attackers, but it doesn't do anything to prevent integrity attacks. So we were able to evict it and then replace it with another cookie that is not HTTP-only. Okay, so we discussed two threat models here. Two threat models are relevant. The first one is the SameSite attacker. That is typically the one where you have an attacker in control of a subdomain. This can happen when you do a subdomain takeover. This is something that has been introduced in 2014 by Detectify, when they showed us how to take over services that were exploiting dangling DNS records. So DNS records pointing to IP addresses of stuff like github.com, and then you could register at github.com your own profile and claim a certain subdomain of another company, okay? In 2021, we published a paper about this, and we tried to make a more systematic study of the issue. We found that this is just insane. Basically, everything is vulnerable. We found more than 900 sites affected by subdomain takeover vulnerabilities, confirmed, like no false positives whatsoever, and more than 1,500 subdomains we could take over. Okay, stuff including CNN, csco.com, F-Secure, Harvard, Renov.com. We also studied the problem of what happens when you have corporate networks or roaming services. For example, now we're using eduROM, right? At the TUVIN, if you use eduROM, you are automatically promoted to a SameSite attacker because you get like a DNS entry that puts you in a SameSite attacker position without mounting any attack, which is just like a bit insane, but that's the way it works. For the network attacker, it's the typical thing. So you have someone in the network who can tamper and read all the unencrypted traffic, so the traffic over HTTP, right? There is a way to protect against this issue. It's an HTTP header called HSTS, stands for HTTP Strict Transport Security, which is a great mitigation, but it has some limitations also at the same time. And the deployment of this header is not so good. Recent measurements from 2022 show that 90% of websites have a partial or missing HSTS deployment. HSTS does something really simple. Like after you connect with your browser to a certain site and there is this header specified, all these subsequent connections must be forced to be performed over HTTPS. So a network attacker cannot do anything anymore at that point. But if you do not include the include subdomain directive, well, then you have a problem because that policy is enforced only for the single origin that you visited, but not for, let's say, like all the subdomains of the site. So you need that, and yeah, 90% of websites are still vulnerable. Okay, so cross CSRF attacks. So cross-site request forgery attacks. I hope everyone knows like what we're talking about here. We're in the context of the same site, so it would not be fair to call them cross-site request forgery attacks. So I prefer using the word cross-origin request forgery attacks. Okay, it's more accurate in this case. So, as we said, in the context of the same site attribute does not play any role. It just bypassed automatically. So we need the tokenization. These, like invisible form fields that are sent along your form submission. That's what we need. And the most typical pattern that we can use for tokenization is called the double submit pattern. It works in a very simple way. The idea is that you have a cookie. So you have, okay, your session cookie that is called in this case s equal to x. And then you have two things. One cookie called the CSRF, and then this invisible input field in your form that you submit, okay? So you perform the request, you send it to the server, one cookie, this post variable, and if the value of these two things is matching, then everything is fine and the request goes through. Otherwise, it's blocked. The wrong assumption in the case of SameSite attackers is that attackers cannot manipulate the cookie. They can only manipulate the token. But that's false, because as we saw before, in the context of a SameSite, you can perform cookie tossing attacks, and then you can just overwrite the CSRF cookie, and then forge an arbitrary request with the CSRF cookie of your choice and the CSRF token of your choice. This request goes through, it's validated by the server, and then you mount the attack. This is known stuff. I mean, it's like nothing new, okay? So a better version of the double submit pattern is called the synchronizer token pattern. And this is a great one that is supposed to be robust against this kind of issues. It works similarly, but the key difference is that you have a CSRF secret that is inside the session itself, okay? Either inside the session itself or cryptographically bound to the session. And then tokens are generated using a function that I call here a generate token that takes this CSRF secret and other parameters. Could be like a timestamp to then, you know, like make these tokens invalid after a while. Validation is very simple. You just like take the CSRF secret that is sent to you to the server in the session. You generate the token again, and then you compare to what you receive via post. And then, if there is an equivalence, then everything is fine, and you can proceed, right? We were interested in checking how the synchronizer token pattern is implemented in web frameworks. And actually, this is something I discovered by just randomly while I was developing a CTF challenge. I screwed up. I was writing the code, then I tested something. I forgot to update some values in my exploit script, and then I got something that was very unexpected. I was like, wait a minute, this is not normal. This should not happen. And so I started investigating what was actually happening in the code. So this is Flask. Flask is a micro framework, meaning that it doesn't do much by itself. If you want functionalities like login management and CSRF protection, you need to get libraries here and there, you put them together, then you ship your app. Two famous libraries for these things are the Flask login and Flask WTF. Yeah, just so I don't say what the fuck. Yeah, it works in this way. So this is also okay, pay attention. This is also a client-side session handling mechanism, meaning that you don't have a file on the server containing the information about the session, but everything is inside the session cookie. Then, this stuff is typically encoded, compressed, sometimes encrypted, and then cryptographically signed. But just for sake of simplicity, just assume that it's like this, okay? This is, exactly how it is after doing all the decryption, the compression, and the coding, but that's exactly that. So, the idea is simple. When you visit, normally, the login page, you get a pre-session. You know that it's a pre-session because the ID is none, so we did not authenticate yet. And we get a token T0. T0 is generated starting from S0, okay? And a secret, but we don't care about that because that's constant. That's always the same one that is stored at the server side. Good, okay? Then we perform the post action to login. So we send also our user and password for the user Bob. Then as you can see, the session is promoted. We get a new token T1 that is generated starting from the CSRF secret S0. And then if we want to perform an action, we send again the session, the CSRF token that we got in the step before, and everyone is happy. Is this okay? I mean, obviously it's not okay. Otherwise I would not be here like giving the talk, right? But do you have any idea why this is not okay? And forget stuff about like, oh, maybe the HMAC, the HMAC is perfect. Okay, imagine that the cryptography here is perfect. So there is a problem here. The problem is that this CSRF secret as 0 is not refreshed upon login. It remains constant there. And the immediate implication of this is what? That tokens that we generated before authentication are still valid after we authenticate, okay? And probably like now we understand like where I want to go and how the attack works in this case. The attack works in the following way. So we have a subdomain attacker, the usual guy at attack.bank.com. The attacker gets a pre-session, so this is not authenticated, with a value S for the CSRF secret, and the CSRF token T0 that is bound to S, okay? Then we perform an unauthenticated session fixation attack, so we set this cookie into the victim's browser. Then the victim performs a login, okay? So the victim obtains a new token T1 that is starting from S, so like it's generated starting from S, and still this is a non-authenticated session. We call it pre-session, all right? And then the victim performs the authentication step for real. So the session now is promoted to an authenticated one, but you can see that the CSRF secret is still S, meaning that now the attacker has a token T0 that is still valid for the authenticated session of Bob. And then like the CSRF, like the CORF attack can go through. We call this attack CORF token fixation. And yeah, it bypasses fault implementations of this pattern that is called the synchronizer token pattern. It's caused by, as we said before, by this CSRF secret not being renewed upon login. It's not needed for the attacker to know the value of S. As we said, it could be encrypted, it could be encoded, it could be whatever. We don't need to disclose the actual value of S because we just needed to let the site do the job for us and give us back the token T0, okay, that is generated starting from the secret. It works in an equivalent way, no matter like if the session handling mechanism is at the client side or more traditionally at the server side. And also like, notice that here we had the assumption that the user is already logged in. Sorry, the user like is not logged in. What happens if the user is already logged in? Well, we can do cookie eviction, and then we de-authenticate the user, or we can redirect the user to the auth endpoint of the site that will just like invalidate the session, and then we can start mounting our own attack, all right? Yeah, so this was more of a, let's say, logical vulnerability. We also studied several other frameworks. This is CodeIgniter 4, that is a famous PHP-based framework with the server-side handling mechanism for sessions. And yeah, this looked perfect to us. This was like really good looking. When I was analyzing it, and my colleague was telling me, like, Marco, I've got an exploit here. Then like we checked the code and everything was perfect. It took us like a few iterations to understand like what was the problem here. And again, we discovered that it was vulnerable because we made a mistake while testing the thing. So it works like this. This is beautiful. So we do an access to the login page, okay? And then we obtain back session ses0 and the CSRF token T0. Ses0 is just like a pointer to the file system of the server where the actual session is stored, okay? And the actual session content is this thing here. You can see the CSRF secret is inside the session, and it's this value, 47BE97, blah, 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 okay? Now, we perform the login, okay? So now Bob authenticates. We got a new session, ses1, pointing to a new file with a new secret S1. And this is not a 47 something something, but it's like 1F5B0, blah, blah, blah. So S1 is different from S0. The secret has been refreshed. All good, right? Sort of. Because also the previous session, the pre-session, got the CSRF secret updated. And they're like, how is it even possible? Well, it's possible because the process under the hood works this way. They started from the pre-session. In the pre-session, they updated the CSRF secret, and then they copied that file into the new file that is the one pointed by ses1. Okay? And yes, I said copied, meaning that the previous session is not invalidated. And the previous session contains now the CSRF secret that is also in the new session that is now an authenticated session under the user Bob. So what can we do now? Well, we can mount this attack. So the attacker at attack.bank.com performs the pre-login session fixation with the session that they got before. Then Bob authenticates with session 0, obtains a new session, session 1, and now the CSRF secret of session 1 is also stored into ses0, okay? But then the attacker doesn't have a valid token for ses1, right? So what can we do? Well, we just ask the server, hey, can you give me a new token? So the attacker just like go to the login page, asks for another token, T2. This one is bound to ses0, but it's also bound to ses1 because the CSRF secret is the same one among like these two sessions, right? And then the attacker can go through because T2 is valid for ses1. So we studied 13 frameworks. We found that 9 of them are vulnerable to different range of attacks. 7 out of them were vulnerable to a broken implementation of the synchronizer token pattern, meaning that these are systemic issues and not just application-specific vulnerabilities. We also discovered that the double submit pattern was enabled by default on 4 of these frameworks, and this is again like vulnerable, like known to be vulnerable, so that was a bit meh. And quite concerning was the fact that 3 of these frameworks were vulnerable to session fixation. Now, session fixation is the worst of all these issues because it can lead to a complete session takeover, all right? And the culprit at least of Express is the library called passport.js that is downloaded like 2 million times a week. And yeah, we found out vulnerabilities there. So they are introduced because of this library that has been fixed now. But 2 million downloads a week, you can understand, you can imagine the ramifications of these vulnerabilities in real-world websites. So yeah, all these problems anyway, like yes, they are application-specific, application-dependent, blah, blah, blah. But at the end of the day, they're always enabled by the fact that cookies have weak integrity. So the question is, can cookies be better? Like just out of the box. Can we just like stop creating like weird things and just have like a secure cookies and game over for the attacker? So we wanted to answer this question. And to answer it, you can't just like reason on cookies in isolation. You need to consider the standard, the browsers, and the servers, because these are all the parties that are involved in the chain. So we proceeded by analyzing the standard, we manually reviewed it, and then we created a testing suite for browsers. We implemented all known attacks for cookie tossing and cookie eviction, and we tested them against Chrome, Firefox, and Safari. And then we did like something similar because we wanted like to check for discrepancies also at the server side, and we wrote a simple differential fuzzer. So the differential fuzzer is simply something where you create a bunch of inputs, okay? But now let's think about like a single one. You give this input to a range of different servers. You try to understand how they parse your own input, and if you can record some discrepancies, then there could be a problem, okay? So we did this, and then every time there was a discrepancy, we went back to the standard to check who was right, who was wrong, and we tried to understand the security implications of these things, okay? So starting from the standard, there are like 2 main changes in the recent years. One is called strict secure. The other one is called cookie prefixes. So strict secure, the idea is pretty simple. and it's a protection against network attackers. So the idea is the following. Imagine that for one site, you have a secure cookie. So a cookie with a secure flag enabled called test, okay? And now, a network attacker tries to do cookie tossing. So tries to set another cookie called test, but from an HTTP origin, so without the secure flag. Given that in the cookie jar there is already one cookie called test with a secure flag, the cookie set by the attacker is discarded, okay? So it's not set in the cookie jar. So yeah, this is a good mitigation against the network attacker threat model. More interestingly, we have the cookie prefixes, which is something a bit ugly because it's not really a flag, but it's like a naming convention, but it works this way. So if you name, if you name your cookies starting with __ host minus and then something, there are additional security protections put in place by the browser itself. Protections are, or like security constraints are, the path attribute must be set to /, it must be secure, and it must not contain the domain attribute, meaning that you have the guarantee provided by the browser that if you have a cookie called in this way, it can't be a domain cookie. And so you have a high integrity in this case because you cannot do cookie tossing with this kind of cookies, because the domain attribute is never allowed if you have this cookie with this naming convention, okay? Good. Now that you know everything about cookies, we have a poll for you. So please, scan this QR code. It's not recrawling, this is safe, really. So scan this QR code and try to answer these questions. So we have several set cookie headers. Set cookie foo equal, set cookie equal foo, set cookie equal foo equal. You need to try to understand, to try to guess whether these headers are accepted by the browser or not, okay? Okay, are you done? We can check the results together. Let's see what you answered. I don't know if it works. 99. What? Oh, come on. Seriously? What? Can I just get the results here, please? Too many participants. Folks, you are too many. I did not plan that. Okay, so, does it work? Yes. Okay, great. So, the first one, the majority of you said set cookie foo equal is accepted by the browser. I agree. I'm with you. Second one, set cookie equal foo, majority of you said it's gonna get discarded by the browser. Yeah, reasonable. Something similar, also for equal foo equal, more or less the same for equal foo. This is very unreasonable indeed. And the last one, yeah, weird stuff, just like foo, okay? So I guess now you're curious to know okay. Okay, so you are right. The first one is accepted by the browser. So GG to you. It corresponds to, so this is the cookie jar. This is the serialized value of the cookie header, okay? And this is our server, in this case, Werkzeug. Werkzeug, that's the way you pronounce it. It's the middleware for Flask-based applications, is parsing it, okay? So this stuff here that is a bit ugly, but anyway, like we can deal with that. It corresponds to a cookie with the key foo, empty value, same thing here, more or less like same thing here. But yeah, I'm sorry to say that you were all very wrong because all these cookies are accepted by the browser, all of them, all of them. And yeah, it's quite concerning because you might ask like, what the hell is a cookie with like, with not a key, with like, there's nothing in the key and there is like something only in the value? And especially, like, look at this. The first cookie corresponds to a cookie with like a key foo and empty value. The third one corresponds to a cookie with not a key, but with a value, and they're serialized by the browser in exactly the same way. Like, what? This is the value that is sent to the server, so I expect the first one and the third one to be parsed in the same way by the server. But unfortunately, all these cookies are parsed in the same way by the server. The reason about this is that Werkzeug thought it was a good idea to just strip leading equal symbols just because, you know. But yeah, this is, this is an issue, like an implementation issue with Werkzeug. But what about the browsers? Browsers were just following the standard. So nameless cookies have been introduced in 2020 in the cookie standard. And this serialization collision that I just presented you is also part of the standard. Because if you have a nameless cookie with a value, then like the serialization in the cookie header is only the value without any leading equal symbol, which is like my brain like exploded when I found out this thing. Security implications, of course, let's bypass everything. So, so we have an host cookie that now we wanted to toss. How can we toss it? Well, easy peasy. From the subdomain, we just create a nameless cookie having as a value __ host minus ses equal to bed. This is not an host cookie. This is a nameless cookie with a very weird value, but whatever, we don't care. We can put like any kind of attribute we have here because the security constraints of host cookies are not enforced at all. How is this thing serialized? Well, good luck to the server understanding like which one is the good one and which one is the cookie that was set by the attacker. Because again, consider that when you serialize the cookie, you don't serialize the attributes. You only serialize the key and the value and nothing else, all right? So yeah. We reported these two things. So first we started a discussion with the standard bodies, and then we realized that, wait a second, you can use this to bypass also like host cookies. So we opened like two separate issues. There was another developer, Axel Chong, who reported the same stuff more or less at the same time. He's credited for these two CVEs, but we discussed like the stuff together. The two issues, like mine and his issues, were merged together, and we discuss other corner cases, mitigations, and so on and so forth. So what's the mitigation here? I mean, not the mitigation, but the solution. Just nuke nameless cookies, because who needs nameless cookies? I mean, I know who, but, so yeah, because like some companies like had some modems sold years ago using nameless cookies, they could not just remove them, and so they decided like to put them in the standard. And so the mitigation of this is that instead of removing nameless cookies, the thing is, if you have a nameless cookie, then the value must not start with a case-insensitive match for __ host minus or __ secure minus, which is just insane because you're adding like so many corner cases to an already very cursed platform like the web, okay? So yeah, anyway, like this thing was fixed, mitigated, call it the way you want. But the case for like strict secure bypass has not been fixed. This is still working, and you can use it to bypass a strict secure cookies. The idea is the same as before. So you have a session equal to good cookie that is secure. From an HTTP origin, we set a domain cookie that is nameless with value session equal to bed. And yeah, it's serialized before the good one. There's like no way for the server to discriminate which one is the secure one, which one is the insecure one. And this is the state of the cookie jar for the browser. You see, one is like a named cookie and the other one is nameless, and it does not have the secure attribute in place. let's talk about PHP. Yeah, so now we have to talk about the server side. We talked about standards, browsers, and now let's have a bit of fun and talk about the server side. PHP. Who knows about the register globals? Raise your hand if you ever heard about the register globals. Okay, some of you, all right. So back in the days when I started with CTFs in 2009, it was really nice because you could just like provide the get variable in the URL, and that if a register globals was enabled, you could have that variable that you specified as a get variable in the scope, in the context of the PHP code as a global variable. Amazing. Now this thing has been removed, but the design of register globals is still affecting PHP-based applications. Meaning that if you provide something like question mark foo.bar equal to buds, this is parsed by PHP in the get super global array as foo_bar equal to buds. Because, you know, dot is not a valid character for an identifier in PHP. Same thing with spaces, and same thing with square brackets. So yeah, what can you do? Well, the thing is that this transformation doesn't only affect get, post, and request, but it affects also the cookie super global array. Such a great idea, right? And this deserves a what? Because again, like when I found out this thing, I was like, why on earth would you do this transformation also like for cookies? I mean, this doesn't make any sense. But yeah, that's the way it was. So how can we abuse this thing to bypass host cookies? Well, I mean, just have a look. All these 3 cookies that are completely different, they are parsed as the same one for PHP. So yeah, I reported this vulnerability, and it was fixed. So now for the space, the dot, and blah, blah, you don't have this problem anymore, okay? So that's all good. That's all good, right? Or not? Okay, so this is so great. Cookie header, foo, open square bracket, bar, close square bracket, buds. How is it parsed by the server? Come on, say the word. Be brave. Say it. Array. Say it. Arrays. Yes, it's an array. You can specify in PHP some cookie values that are parsed as an array, meaning that there is probably a different code in the PHP code base that takes care of like doing this parsing here. And maybe this is not affected by the register globals shenanigans anymore, but this is like something else. Guess what? If you send this thing, well, this is still vulnerable. It's still vulnerable nowadays. I reported this thing in November 2022. The submission form for bugs in PHP is just horrible. So there was like no way to track like any progress, whatever. So yeah, I checked it out yesterday night, and I figured out that yeah, it's still vulnerable. So I reported it again yesterday, and hopefully they're gonna fix it at a certain point. Yeah. Two last things. The synchronization issues. These are problems that affected Firefox. Not really like super interesting or like super impactful, but like very interesting in any way. So the first one affects a protection for this strict secure mechanism. Okay, so imagine that you have https://bank.com setting a secure cookie with the value good. Okay, then you have http://bank.com setting a non-secure cookie via JavaScript. Your expectation is that this cookie is not set because of strict secure. That is like what we found before. And this is indeed true. The cookie is not set, but you can get it back if you call document.cookie from the HTTP origin. And then it was like, this is so weird because like it's not in the cookie jar, but only accessible via the getter of document.cookie. And by digging into the issue, we figure out that this is due to another security mechanism that is the site isolation for Firefox. So you have like two different processes, and because of a lack of communication, okay, it was not possible for the HTTP one to infer the state of the HTTPS one, and that's why from JavaScript you can still read it. The last of the synchronization issue, again in Firefox, was when you perform a cookie jar overflow. We found out that our test resulted in a corrupted state in Firefox. We could bypass the limit of cookies that you could set via JavaScript. And these cookies that you can set and are retrievable via the API document.cookie cannot even be deleted using the set cookie expiration, with an expiration date in the past header, clear site data, or even manually. You can open like the developer tools, you remove them, and you can still get them back if you call the document.cookie API. Implications about this are for these JavaScript libraries, front ends, that trust the value returned by document.cookie to then populate HTTP request headers, for example. Also, like by preparing this presentation yesterday, I figured out that we got a CVE for this that I didn't even know about. According to NIST, this is a high vulnerability, 7.5 score, whereas it's absolutely like not that impactful. And I agree with the Mozilla that this is like a low impact vulnerability. But yeah, that's content for another talk about the CVEs, CVEs, and so on and so forth. So yeah, thanks a lot for your attention. That's the way the cookie crumbles. A couple of takeaways. I'm used to the web being in a terrible security state. I mean, I'm not surprised anymore. But when we found these vulnerabilities on battle-tested web frameworks and libraries, you know, this was very concerning. I did not expect to find out this. The question is then, like, why do we have like still these vulnerabilities? Is it like a lack of understanding of the threat model? Or what? Or maybe it's just like a compositionality issue when you take like libraries together that do not know like what the other one is doing, you know? I don't know. And now we are also like measuring the ramifications in the wild. We're doing like a measurement study involving automatic logging in on websites to understand these issues more precisely. Second problem that we already discussed is like legacy design. Again, I'm okay with applications behaving in a legacy way because you don't want to break the internet. But why are we letting legacy design creeping into standards? This is insane. This should not happen. We discussed about nameless cookies, but it's not limited to that. Some of you probably remember the 2 minutes exception rule for same-site cookies without the same site attribute. Yeah, that was like that has been introduced as a hack by Chrome. There's something that should have been like removed pretty soon. Now it's part of the standard. Okay, it has been standardized, and the 2 minutes is also the recommended value in the standard. So standards are not like leading the way. Standards are just reflecting implementations, and this is problematic. The last point, that is something that I understood while discussing with developers, is that they are completely out of pace. They cannot keep track of all the changes of the web platform. It's unsustainable for them, and we need the platform to, you know, like put together developers, browser vendors, and editors of web standards. Please like have a look at the paper, artifacts. There is a bunch of other stuff that I didn't have time to discuss today. And yeah, if you have any questions now or like even later, we can have a chat. And thanks a lot for your attention.
Hi, so what is the intended purpose on nameless cookies? Where would I use that?
The intended purpose is not to break some modems from Verizon. And this is public information. So if you go to on GitHub, there are a lot of issues that track the discussions, interactions between web developers, browser vendors, and editors of the web standards, discussing like how to improve, you know, standards. And if you dig enough, you will find that there is like the discussion about Firefox try like to remove nameless cookies from the browser. And then they broke some stuff. And then they tried like to figure out what they broke. It was like this Verizon modems. And instead of fixing the modems, they introduced this stuff in the standard.
Okay, I see.
So at least like the behavior of Chrome and Firefox was aligned. Then Safari also like stepped in and said like, okay, sounds good to us. We will follow the same way that you're doing. So we will harmonize our implementations to respect the standard. And they never change the behavior. So Safari is not vulnerable to nameless cookies-based attacks. But not because like they made a conscious decision. They just forgot to apply the change that they promised doing. I mean, this is the state of things in the web.
Yeah. Thanks.
Hi, congratulations for the presentation. And what about JWT cookie?
Okay, so JWT tokens. That's like a question that I get every time. Like, okay, cookies are bad. Shall we use like something different, right? I mean, you can, but then you are implementing your own solution with a bunch of other pitfalls that could be like specific to your case. With cookies, you already have a lot of protections by default if you use, for example, like host cookies. And if you're reinventing the wheel by yourself and you want the same capabilities that you can achieve with cookies, you must be extremely careful in what you're doing. So it's not like the, holy grail of web security, moving to JWT tokens. It could work, but it depends. It has some limitations, and again, you are on your own at that point. So if the question is like, will we ever get rid of cookies? I don't know. That's my honest answer.